Let's discuss stable isotopes. They are incredibly useful because they fractionate by mass. That's a temperature-controlled process, so we can use them to calculate temperatures of different processes. And we can also use them as geologic tracers. This image is of annual layering called varves that are seen in a tropical ice cap. And each of these layers represents an entire year's worth of snow accumulation, and we can use stable isotopes to look at seasonal variations or annual variations in global temperatures based on how the oxygen isotopes have fractionated within those layers. So there are many elements of low atomic weight that have two or more stable isotopes. For example, hydrogen, that is hydrogen, deuterium, and tritium. There's carbon 12 and 13, nitrogen 14 and 15, oxygen 16, 17, and 18, and 4 isotopes of sulfur. We won't cover all of these in this lecture, but we will hit some main topics. The different masses cause the isotopes to behave differently in physical and chemical processes. For example, hydrogen 2, or deuterium, paired with oxygen 18 is much heavier than hydrogen paired with oxygen 16 and will be left behind during evaporation. Stable isotope geochemistry is concerned with variations of the isotopic compositions of elements arising from physiochemical processes, and that's versus nuclear processes. Fractionation refers to the change in an isotope ratio that arises as a result of a chemical or physical process. That fractionation occurs during isotopic exchange reactions in which the isotopes are redistributed among different molecules containing that element, unidirectional or incomplete reactions, physical processes like evaporation and condensation, melting, crystallization, adsorption, desorption, or diffusion. And the characteristics of a useful stable isotope system are, one, that they have a large relative mass difference between stable isotopes, two, that the abundance of the rare isotope is high, so we're talking about 0.1 to 1%, and three, that the element forms a variety of compounds in a natural system. And below are listed several different useful stable isotope systems. And just notice that the convention is that the heavy isotope is put above the light isotope in these ratios. The degree of isotope fractionation depends on the relative weights of the isotopes. Commonly fractionated elements include hydrogen, carbon, nitrogen, oxygen, and sulfur. Isotopes that are somewhat fractionated include silicon, iron, and chlorine. And the isotopes where fractionation is impossible are beryllium, fluorine, sodium, aluminum, and phosphorus. Isotope fractionation during chemical processes is caused by exchange reactions of the type shown below, where carbon dioxide exchanges with water that includes oxygen 18 to give us carbon dioxide with the oxygen 18 plus water. At equilibrium, we have, for the preceding reaction, an equilibrium coefficient that is equal to the square root of carbon dioxide, in which we've got oxygen 18 times water, divided by the square root of carbon dioxide with oxygen 16 times water with oxygen 18. We use molar concentrations and not activities because the activity coefficients cancel out. If carbon dioxide and water did not discriminate between oxygen 16 and oxygen 18, then the coefficient K would be equal to unity, so K equal to 1. However, at 25 degrees Celsius, K equals 1.0412, which implies that carbon dioxide slightly prefers oxygen 18 and water prefers oxygen 16. That preference is small, but it's large enough to cause isotopic fractionation. Why is K not equal to 1? Because O18 forms a stronger covalent bond with carbon than does O16. The vibrational energy of a molecule is given by the equations. The vibrational energy is equal to 1/2 of Planck's constant h times the vibrational frequency. And the vibrational frequency is equal to 1 over 2 pi times the square root of the Boltzmann constant k divided by the mass. Thus, the frequency of vibration depends on the mass of the atoms, so the energy of a molecule depends on its mass. The heavy isotope forms a lower energy bond, but it does not vibrate as violently. Therefore, it forms a stronger bond in the compound. The rule of Baggelisen in 1965 said that the heavy isotope goes preferentially into the compound with the strongest bonds. Mass differences also give rise to fractionation during physical processes, so diffusion, evaporation, freezing. Fractionation during physical processes is a result of differences in the velocities of isotopic molecules of the same compound. Consider molecules in a gas. All molecules have the same average kinetic energy, which is a function of temperature. So the kinetic energy is equal to 1/2 the mass times the vibration frequency squared. Because the kinetic energy for heavy and light isotopes is the same, we can write the vibrational frequency of the light isotope divided by the vibrational frequency of the heavy isotope is equal to the square root of the mass of the heavy isotope divided by the mass of the light isotope. In the case of C12O16 and C13O16, we have the vibrational frequency of the light isotope divided by the vibrational frequency of the heavy isotope is equal to 1.0177. Regardless of the temperature, the velocity of C12O16 is 1.0177 times that of C13O16. So the lighter molecule will diffuse faster and evaporate faster. Regarding kinetics, lighter isotopes form weaker bonds in compounds, so they are more easily broken and hence react faster. Thus, in reactions governed by kinetics, the light isotopes are concentrated in the products. At high temperatures, the equilibrium constant for isotopic exchange tends toward unity. That is, as temperature increases towards infinity, K increases toward 1. Because small differences in mass are less important when all molecules have very high kinetic and vibrational energies. So at colder temperatures, isotopes will be more heavily fractionated. The isotope fractionation factor is defined as alpha, that equals the ratio of one isotope in phase A divided by the ratio of the same isotope in phase B, where the ratio of A and B are the isotope ratio of two phases, for example, carbonate and water or water vapor and water. We can consider a reaction with liquid water and water vapor at 25 degrees C. The fractionation factor for oxygen in liquid water versus water vapor is the ratio of the oxygen isotopes in the liquid water divided by the ratio of the oxygen isotopes in the water vapor, and that equals 1.0092. The differences in isotope ratios are relatively small and are expressed as parts per thousand, or per mil, deviations from a standard delta, sometimes called del. If delta is greater than 0, that means that the sample is enriched in the heavy isotope relative to a standard. If delta is less than 0, that means that the sample is depleted in the heavy isotope relative to a standard. The relationship between the fractionation factor and delta is the fractionation factor between phase A and B is equal to delta A plus 1,000 divided by delta B plus 1,000. The fractionation factor is a function of temperature. So 1,000 times the natural log of the fractionation factor between phase A and B is equal to a constant A times 1,000,000 divided by temperature squared plus a constant B. This graph shows the experimentally determined equilibrium oxygen isotope fractionation factors for several mineral and water pairs as a function of temperature, with the fractionation factor on the y-axis and temperature on the x-axis. And what you can see is that the fractionation factor varies inversely with temperature. That is, the fractionation factor is larger at lower temperatures. This graph shows the experimentally determined equilibrium carbon isotope fractionation factors as a function of temperature. And again, the fractionation factor varies inversely with temperature. And this shows, from the top down, dolomite, calcite, diamond, graphite, and several carbonate species. There is a useful approximation when looking at the fractionation factors and the delta values for these systems. Natural logarithms of small numbers like 1.00x have the property that 1,000 times the natural log of 1.00x is approximately equal to x, as long as x is less than or equal to 9. This approximation holds for a fractionation factor between phase A and B for carbon, nitrogen, oxygen, and sulfur isotopes in many systems. And this leads to the following. 1,000 times the fractionation factor between phase A and B minus 1 is approximately equal to 1,000 times the natural log of the fractionation factor between phase A and B is approximately equal to the delta value of phase A minus the delta value of phase B, which is equal to the difference between phase A and B. So that we can simplify these relationships and say that 1,000 times the natural log of the fractionation factor between phase A and B is approximately equal to the difference in the isotope value between phase A and B is approximately equal to constant A times 1,000,000 divided by temperature squared plus the constant B. Each isotopic measurement is reported relative to a standard, and here we can define a measurement reporting convention. These are in delta units. So the delta 018 value can be calculated using the isotope ratio in your sample minus the isotope ratio in your standard divided by the isotope ratio in your standard times 1,000. Or we can write that out as being the 018-016 ratio in your sample minus the 018-016 ratio in your standard divided by the 018-016 ratio of your standard times 1,000. This works the same for carbon and deuterium. And note that we don't write out the ratio for the deltas. We simply write delta 018, delta carbon 13, and delta deuterium. The standards that we use are for hydrogen or deuterium, and sometimes for oxygen are SMO, or standard mean ocean water. For carbon and sometimes oxygen, we use PDB, which is the PD belemnite. And for others, like lithium and boron, and some of these standards are themselves calibrated to standards with the National Bureau of Standards, NBS. And each of those standards is given a number, like NBS 951. And nitrogen is calibrated to atmospheric nitrogen. The standard for sulfur is CDT, which is the Canyon Diablo meteorite from Meteor Crater in Arizona. Evaporation of surface water in equatorial regions causes the formation of air masses with water vapor that is depleted in O18 and deuterium compared to seawater. This moist air is forced into more northerly, cooler air in the northern hemisphere, where water condenses, and this condensate is enriched in O18 and deuterium compared to the remaining vapor. The relationship between the isotopic composition of liquid and vapor is equal to the fractionation factor between vapor molecule times delta O18 value of the vapor plus 1,000 minus 1,000. Assuming that the O18 value for the water vapor is minus 13.1 per mil, and the fractionation factor between the liquid water and the water vapor is 1.0092 at 25 degrees C, then we can work out what the delta O18 value for the liquid water is. We plug in the fractionation factor times minus 13.1 plus 1,000, and then subtract 1,000 to get minus 4.0 per mil. Assuming that delta deuterium of the water vapor is minus 94.8 per mil, and the fractionation factor between liquid water and water vapor of hydrogen is equal to 1.074 at 25 degrees C, then delta deuterium of the liquid water is equal to 1.074, that fractionation factor for hydrogen, times minus 94.8, the delta deuterium value for water vapor, plus 1,000, then subtract 1,000 to get minus 27.8 per mil. These equations give the isotopic composition of the first bit of precipitation, as O18 and deuterium are removed from the vapor. Thus, the remaining vapor becomes more and more depleted. And the delta O18 and delta deuterium values become increasingly negative with increasing geographic latitude and altitude. So if we say the delta value is greater than 0, the sample is enriched in the heavy isotope. If the delta value is less than 0, the sample is depleted in the heavy isotope. There is fractionation taking place with this evaporation and precipitation. If we look, for example, at a coastal region where water is being evaporated from the ocean, and we start off with a delta O18 value for ocean water of 0 per mil, a delta deuterium value for ocean water of 0 per mil. With evaporation, we leave behind some of the O18 and deuterium to get values of O18 of minus 12 per mil and delta deuterium of minus 87 per mil in the water vapor. And the first precipitation that comes out of that water vapor, we will get a delta O18 value of minus 3 per mil and a delta deuterium value of minus 14 per mil. So raining out preferentially the heavy isotope. The remaining vapor then has an O18 value of minus 15 per mil and of deuterium of minus 112 per mil. We have a second precipitation as we go over a mountain range, and the rain has a delta O18 value of minus 11 per mil, and the deuterium has a value of minus 31 per mil. So that second precipitation event has, again, fractionated the isotopic values in the water. The final vapor has a delta O18 value of minus 17 per mil and deuterium of minus 128 per mil. So we see progressively depleted O18 and deuterium values as we go inland, and we see progressively depleted rainfall values as we go inland. If we look at a map of North America showing contours at the approximate average delta deuterium values of meteoric surface waters, so in lakes and streams, we see progressive depletion in the deuterium values as you go north in latitude and as you go inland over mountain ranges, like the Sierra Nevada. If you plot the variation in O18 values versus mean annual temperatures in different areas, you'll see that there's a good correlation with more depleted O18 values here at the South Pole with the mean annual temperature. Here are some areas in Greenland and northern Canada. Here's Copenhagen, Dublin, and Barbados up here. So it's clear that there's a temperature control on the fractionation of oxygen isotopes. Let's look at what we can learn from snow and ice stratigraphy. The plot on the left shows seasonal variations in snow and firn at a certain location in the South Pole, where they're measuring the O18 values at different points along the snow and ice cores. And you'll see that there's good correlation between the delta deuterium and the delta O18 values. So less depleted peaks in the same years, more depletion in the same years, corresponding to depth. And here, this would let us look back in time, tens of thousands of years, to look at global temperature variations. These plots show the O18 values of foraminifera in Pacific and Caribbean sea cores. And on the bottom, this shows a variation in the paleo-temperatures calculated from O18 values over the last several 100,000 years. And what I want you to notice is that there's a good correlation in increases and decreases of these values over time. We can use the O18 data from cores, and what I want you to see is that these O18 curves that are taken from samples from cores, and the deeper down the cores you go for those samples, the farther back in time you're moving. And this correlates to these paleo-temperatures that are calculated from the O18 data. And what we see in this set of foraminifera data, and this is from the equatorial Pacific, around 16 million years, there is a decrease in the O18 values, which corresponds to a decrease in temperature of the bottom water at that site. And it was associated with the growth of continental ice sheets in Antarctica. Because both hydrogen and oxygen occur together in water, the O18 values and delta deuterium values are highly correlated, as you've already seen. And this gives us a meteoric waterline. So on this plot we have the delta deuterium values, and the x-axis we have the delta O18 values, and along this line here is the meteoric waterline. It's calculated from this equation that correlates the delta deuterium values and delta O18 values, and we can use it to show whether samples are from high latitudes, low latitudes, or whether samples deviate from that meteoric waterline. And this ellipse represents the standard mean ocean water. So for example, here's the delta deuterium and delta O18 plot of samples from the northern hemisphere that are taken from different places, including from an iceberg, from Whitehorse, Canada, from Edmonton, Canada at lower latitudes, down into Flagstaff, Chicago, Tokyo, and through to New Delhi and Bombay. So meteoric waters fall along that line and correspond to those latitudes. Any deviations from the meteoric waterline represent additional fractionation that affects oxygen and deuterium differently, or one to the exclusion of the other will skew a water away from the meteoric waterline plot. Those effects can include elevation effects. We see differences in delta deuterium of -8 per mil for every 1,000 meters, or -4 per mil for every degree Celsius. We can see effects from temperature because the fractionation factor is different, evapotranspiration and steam loss, or water-rock interaction because there's little hydrogen in most rocks. And these processes follow Rayleigh distillation, and this describes isotopic fractionation that occurs during condensation in moist air masses. And the Rayleigh equation that governs this process is this. The RV value is the isotope ratio of the remaining vapor. The RVO value is the ratio for the initial vapor. F is the fraction of the vapor that's remaining. And alpha represents the isotopic ratio in the liquid divided by the ratio in the vapor. The effect of Rayleigh distillation on the O18 value of water vapor remaining in the air mass and of meteoric precipitation falling from it at a constant temperature of 25 degrees Celsius follows this plot, where we see the vapor increasingly depleted and the liquid phase increasingly depleted in O18. And on this end, this is as the fraction of the vapor that's remaining decreases. And overall, this tells us that delta O18 is increasingly negative with continued precipitation. Some complications arise, however, from re-evaporation or because of the temperature dependency of the fractionation factor. We can look at some examples of isotopic fractionation in clays. Oxygen in igneous and metamorphic rocks is enriched in O18 relative to SMO. And when those minerals react with acidic meteoric waters during weathering to form clays, the amount of isotopic fractionation depends on some other factors, including the isotopic composition of the meteoric water, the isotopic composition of the original minerals, the water-to-rock ratio, the temperature, and the fractionation factors for all of these. To form clays, you need a high water-to-rock ratio. So the oxygen isotope composition will be dictated by that of the meteoric water. The composition of the rock will actually have little influence. Similar remarks apply for hydrogen isotopes, except that igneous and metamorphic rocks are depleted in deuterium relative to SMO. We find that the following equations relate delta deuterium and delta O18. For montmorillonite, we have an equation of delta deuterium is equal to 7.3 times the delta O18 value minus 260. For kaolinite, delta deuterium is equal to 7.5 delta O18 minus 220. Once the clays are formed, they don't re-equilibrate unless they're heated to above temperatures around 100 degrees Celsius for hydrogen, or temperatures above 300 degrees Celsius for oxygen. This is another schematic representation of the isotope composition of hydrogen and oxygen in the clay minerals that formed from meteoric waters. And here is the meteoric water line for reference. And what we see is this deviation in cool and in warm environments that correspond to low and high latitudes, and soils that form from these clays or with these clays fall in this region that includes clays and aluminum and iron hydroxides. And you see even a difference in the clays that form, montmorillonite forming in the cooler environments and kaolinite forming in the warmer environments. The isotopic values for primary magmatic water that might interact with these rocks fall in this area. And the metamorphic fluids that include water would fall in a region of 300 to 600 degrees Celsius in this range of isotope values. And as I've said, we use these oxygen isotope values to calculate paleo-temperatures in a variety of environments. The fractionation of oxygen isotopes between calcium carbonate, for example, foraminifera, and water is used to determine the seawater temperature at which the mineral is formed in the examples that I showed you. There's a basic assumption that the mineral that's crystallized at equilibrium was not subsequently altered. This gives climate information for the last 100 million years. And climate changes lead to changes in the ocean water chemistry. Animals that live in that ocean water and make their shells out of the calcium carbonate that they get from the calcium, carbon, and oxygen from the water are going to reflect those changes. And we can measure the oxygen isotope values for their shells after they die, fall to the sea floor, and comprise the sediment that we can later drill a core of. We can use the fractionation of oxygen isotopes among coexisting minerals as a geothermometer. It has to be assumed that the minerals crystallize at the same time, at equilibrium, so under the same conditions, and that they were also not altered subsequently. And if the fractionation of oxygen isotopes between several mineral pairs give us the same temperatures, then we have more confidence that the temperature estimate is correct. Here's an example in which a hydrothermal vein comprised of quartz, calcite, and chlorite were deposited together. The minerals were analyzed for their oxygen isotopes. It resulted in a delta O18 value for quartz of 5.1 per mil, for calcite of 3.8 per mil, of chlorite of minus 1.5 per mil. And we assume that these three minerals were all in equilibrium. And when I say equilibrium, I don't mean that their values are equal. Clearly, the values are not equal. Equilibrium implies that they formed at the same temperature conditions, that they were growing at the same time, etc. Those conditions were held constant, and so these minerals should have fractionated the O18, O16 according to whatever conditions they were in. First, we need to calculate the fractionation factors for these minerals, and we do that following the equations that I've showed you already. And we can simplify those equations because we are dealing with the natural logs of small numbers. We can get down to a simple equation that shows us the difference between the delta O18 values of different minerals. So for the difference between quartz and water, calcite and water, and chlorite and water. When we work out these problems, we're following those very same equations that I will ask you to follow in class. And we end up with a value for the difference between quartz and calcite of 1.3 per mil. We can use that to calculate the temperature, so relating the temperature squared to this value, and work out a temperature of 576 degrees Kelvin. We need to change from degrees Kelvin to degrees Celsius, and we end up with about 303 degrees Celsius. We follow the same equations for the relationship between quartz and chlorite, and we end up with 6.6 per mil. We relate 6.6 per mil again to this other side of the equation, to T squared, and calculate a temperature of 586 degrees Kelvin. I'm just reminding you that you're getting Kelvin out of this equation. You need to take your degrees in Kelvin, subtract 273.15 degrees to get your answer in degrees Celsius. we end up with a temperature of 313 degrees Celsius, and it's similar to the first mineral pair, 303 degrees Celsius. We follow the same method for calcite and chlorite. We calculate 5.3 per mil and end up with 318 degrees Celsius. Again, very similar to the first two temperatures. The average we get is 311 plus or minus 8 degrees C. And within the error that we've got, these values are identical. And that gives us confidence that the minerals are deposited at the same time in equilibrium at the same temperature. Previously, I talked about the constants A and B that you plug in to these equations to calculate temperatures from differences in the O18 values for different mineral pairs. For quartz and other mineral pairs, so quartz albite, quartz jadeite, quartz anorthite, etc. These are all experimentally determined. This plot compares the value of capital delta O18 values with temperature, where the delta O18 value is the difference between the little delta O18 values of two coexisting minerals that have equilibrated oxygen with the same isotope reservoir at the same temperature. In this case, this is quartz magnetite, albite magnetite, anorthite magnetite, and quartz calcite. So this will work to calculate temperatures for mineral pairs, assuming that you're finding them in the same rock and that you see textures that tell you they grew at the same time. Overall, there's a typical range of delta O18 values for igneous rocks versus meteorites. We see pegmatites that are most enriched in O18, followed by granitic rocks, gabbros and basalts, ultramafic rocks. And the achondrite and chondritic meteorites have a value of about 5 to 6 per mil. And so this is what you would expect for about a mantle oxygen isotope composition. That's why it's similar to the chondritic meteorites and to ultramafic rocks. We can look at a broader compositional range of O18 values for different rock types. We see Earth's mantle here at 5.7. We see increasing enrichment in O18 from mantle compositions to felsic compositions in igneous rocks. We see a wide range in metamorphic rocks, a wide range in sedimentary rocks. Seawater is our standard, and so it has a delta O18 value of 0 because we're using SMO. Meteoric waters are more depleted in delta O18 compared to the rocks. Notice that metamorphic waters are more enriched in delta O18. And so there will be significant differences if we're interacting meteoric waters with rock versus metamorphic waters. Let's take a look at a different isotopic system. These are stable sulfur isotopes, sulfur 32, 33, 34, and 35, but the fractionation between 32 and 34 is the most studied. And as with the oxygen isotopes, the formula that we use to calculate the delta sulfur 34 values, look at the ratio of 34 to 32 in the sample minus that same ratio in the standard, divided by the ratio in the standard times 1,000. The most important cause of sulfur isotope fractionation is the metabolism of the bacteria Desulfovibrio and Desulfatum maculum. These bacteria flourish in anoxic, meaning without oxygen, anoxic environments by oxidizing organic matter using oxygen from sulfate. The sulfate is reduced to H2S, which is enriched in sulfur 32 relative to sulfate. This is the sulfate reduction reaction. We see that we have methane plus sulfate ions plus hydrogen ions react to form H2S, carbon dioxide, and water. For this reaction at 25 degrees C, the delta Gibbs value is minus 26.324 kilocalories per mole, or log K equal to 19.3. So the reaction is highly favored thermodynamically because it has a low delta G value, but it's slow in the absence of bacteria. The reaction is not at equilibrium, and a large kinetic isotope fractionation factor between sulfate and sulfide occurs when bacteria are involved. The extent of fractionation of sulfur isotopes between sulfate and sulfide depends on 1. The rate of metabolism by bacteria, 2. The composition and abundance of the food supply, 3. The size of sulfate reservoir, the temperature, and the rate of removal of H2S. There are alternative scenarios. This could be a closed system where the concentration of H2S may build up until it poisons the bacteria, as in the Black Sea. The H2S is then strongly depleted in sulfur 34. Or if it's an open system, the sulfate reservoir is virtually infinite and H2S is removed. The metabolized sulfide is depleted in sulfur 34, but the isotope composition of sulfate remains constant. If it's an open system that is sulfate limited, H2S is free to escape, and Rayleigh distillation occurs, and the remaining sulfate and each new batch of H2S becomes enriched in sulfur 34. These are the distribution patterns for delta sulfur 34 values of H2S and sulfide minerals when the sulfate of delta sulfur 34 is 20 per mil, is reduced by various mechanisms. We have very depleted sulfur 34 values in euxinic or anoxic environments. We have shallow marine and brackish environments, or environments where there's decomposition of organic compounds, where we have organic reduction or inorganic reduction. We can use sulfur isotopes as tracers. Metabolic H2S can react with metals and form sulfides. These generally have a delta sulfur 34 value less than 0, but this can vary stratigraphically, and it may even be greater than 0, depending on the extent of Rayleigh distillation. Thus, sedimentary and igneous sulfides tend to exhibit different trends in their delta sulfur 34 values. Sedimentary sulfides have sulfur 34 values that show a wide range of values, generally toward negative values, so depleted in sulfur 34. Igneous sulfides have values that are close to 0 per mil. If we compare sulfur isotopes from a variety of environments, we see meteorites near 0, igneous sulfides averaging near 0, sedimentary sulfides are depleted in sulfur 34, and then we have enriched sulfur values in ocean and evaporate sulfides. There are caveats. We need to be careful in using sulfur isotopes as tracers because delta sulfur 34 values of some of the sedimentary sulfides can be near 0 or positive. The sulfur values of some magmatic sulfides could be negative if the sulfur originally came from sedimentary rocks that were melted. Sulfur 34 values of igneous rocks can vary from 0 depending on the pH and the partial pressure of oxygen. And sulfur 34 values of sulfides in igneous and metamorphic rocks can be changed by isotope exchange during alteration. This plot shows the variation in sulfur isotopes at the top and strontium values at the bottom in the Phanerozoic. Note that both the sulfur 34 values and the strontium ratios decline irregularly during the Paleozoic. from the Cambrian to the Permian. During the Mesozoic, both parameters had low values, but began to rise during the Cretaceous and continued to rise in the Tertiary. Those variations in isotopic compositions in the oceans were caused by global changes in the geochemical cycles of these elements. We can use the sulfur isotopic composition in sulfide and sulfate minerals as geothermometers if all the minerals precipitated at the same time in equilibrium with one another. For example, we can consider the fractionation between galena and sphalerite. Following those same equations, we can calculate a sphalerite-galena difference in sulfur isotope values of 4.0 per mil. From that, we can calculate a temperature of 151 degrees Celsius. This graph shows the fractionation factor for sulfur isotopes as a function of temperature. And we see values that are close to zero for some minerals, pyrite, chalcopyrite, sphalerite. And we see a range from negative to positive slopes in the relationship between the fractionation factor and temperature. Now let's switch to carbon isotopes as tracers. These are typical carbon isotope values for meteorites, ranging from near mantle values, about -5, to very heavily depleted in carbon-13. Atmospheric carbon is somewhat depleted in carbon-13. Remember, we're using the PD belemnite often as a standard, and that's a marine cephalopod. And so marine values of carbon isotopes are near zero, as marine limestones. Generally, sedimentary rocks are highly depleted in carbon-13. And we see carbon values near mantle values in carbonatites and diamonds that come up in kimberlites, because those are bringing up mantle xenoliths in those volcanoes. Now, while I say that, look at the range of values seen in all kimberlites. They are generally very heavily depleted in carbon-13. So some of those carbon isotope values in kimberlite volcanoes are reflecting the mantle nature of the kimberlites. And we're also seeing very heavily depleted carbon-13 values that look a lot like sedimentary values. And that's because we recycle sedimentary rocks down subduction zones into the mantle. Here is the first kimberlite mine. This is the big hole that was dug in the 1800s in Kimberley, South Africa, hence the name kimberlite for these volcanoes. You see the structure of the volcano has very discrete sides, and so they literally dug down, straight down, the diamond-bearing material in these volcanoes. They are not impressive volcanoes, and will show you a little bit about this because most of you probably haven't heard about kimberlite volcanoes unless you've taken a class with me before. They look a bit like this. They have virtually no topographic or geomorphic expression, and the way that they are found generally is to see pyrope garnets that have these deep purple color because they are very rich in magnesium, and chrome diopsides that are bright green from the chromium in them. Some of the most recent kimberlite finds in Canada have actually been from finding those minerals in soils. And just because you may be curious, Kimberlites are generally found in Siberia, South Africa, India, Brazil, northern Canada, and there are some other places where kimberlites or kimberlite-like volcanoes have erupted and brought up diamond-bearing material. Let's talk briefly about chlorine isotopes. There are 9 isotopes of chlorine and only 3 occur naturally. That's chlorine-35, chlorine-37, and radioactive chlorine-36. Chlorine-36 decays to sulfur-36 and argon-36 with a combined half-life of 308,000 years, making it suitable for dating in the range of 60,000 to 1 million years. Large amounts of chlorine-36 were produced by irradiation of seawater during atmospheric detonations of nuclear weapons from 1952 to 1958, making it an event marker in soil and groundwater. This is useful for dating waters less than 50 years before the present, and it's used in dating ice and sediment. Chlorine is generally useful in hydrologic studies because it's highly soluble. It exists in nature as a non-sorbing ion. It does not participate in redox reactions. It has quickly identifiable sources, for example, seawater. Chlorine-35 and 37 are highly mobile but not easily fractionated in nature. But fractionation can occur during diffusion-controlled processes in groundwater, during high-temperature water-rock interactions, or as a result of ocean temperature variations over time. Chlorinated contaminants, so for instance, industrial solvents like TCE or PCA, have a distinct isotope signature, making chlorine isotopes useful in identifying sources of contamination.